Okay, so let me come to x of 5. Then that is part 3. And they're talking about a language, L3. And L3 is the language which contains strings of this alphabet. And they're saying that these strings, they must contain at least one A. Yeah, they can contain lots of A's, but at least one. So we can have 1, 2, 3, and forever. You get it? So let's come and see what's happening. Here. So when you have a language that contains at least A, do you notice that A is in this language? Yeah, because a string that contains at least one A is correct. So the simplest string in this language is A. So come and draw my automaton. Do that. Then I have a state. I'm going to call it accepting. That is when I see an A. You get it? Now, what is happening here is 1. When I see a B or a C, I stay in this state. I don't come to this accepting because I haven't seen A. The language must contain at least an A. I think it makes sense now. You see? The language must contain at least an A. So, what I want... no! I nearly hurt my arm. So when I see a B or a C, I keep waiting in this state because it is not accepting. So whenever we read a string that doesn't contain any A, we're going to stop in this state. But after we see an A, then we accept anything that comes after because we have seen one A. You get it? Yeah, this is it. So the grammar for this language is the production rules, that is S. When I'm in S and I see a B, I come back to S. And when I see a C, I come back to S. And when I see an A, I go to A. You get it? Now, when I'm in A and I see an A, I stay in A. I see a B, I stay in A. I see a C, I stay in A. But what is interesting is this is an accepting state, so we have this here. Now this grammar is stupid correct. Now I know there may be some folks out there who are saying, but Kasozi, if this is A, 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 this is and this is A, why can't we just come and bring these boys up here and we get rid of that? But I won't explain that for now. But when you see this language, S gives us A, this gives us A. But when you see S, S gives us BS, which is not here. It gives us CS, which is not here. Now, which means that this grammar must be the way it is. Okay, now this is a type 3 grammar. I told you what are type 3 grammars. Type 3 grammars are grammars whereby we have A, and A equals to alpha, B, or A is equal to alpha. You get it? And what is happening now is from the definition they say A and B must belong to the set of variables. Variables are just the states. And alpha must be this one. You get it? You get it? Wait, let me first reply to this lady. Let me reply to this lady. I get back. Wait. Oh, I'm making some videos here. Good. But what does this mean? Sorry. T star simply means I'm having high caps now. T star means T0 union T1 union T2. Now, if I have my strings, if I have a set of strings T, you get it? And T is containing A and B, then T of 0 is what? It's epsilon. T of 1, no, it's the same as this one here. The set of all strings over this alphabet that have length 1, and now T of 2 is A, B, and B, which means we can have a grammar of this kind here, whereby we have our A, and A goes to what? Now alpha can be anything of this, or anything, because this one goes on forever. So we can have a language like this, then we have a B. And we can say now my alpha can go to anything else. Let me say it can go to AB. Anything. So this grammar you are seeing here is called a type 3 grammar because it follows this form here. And now we see something interesting. The variables, these capital B's, are on the right. In French, it is this. So this grammar is a type 3 grammar that is called right linear grammar. Cool. Now if the B's, if the variables, those capitals are on the left, like this, for example, you have a language whereby we have not a language, these production rules like B, A, and A, B. Now since the variables are on the left, we call this one a left linear grammar. Now right linear grammar and left linear grammars are just two categories of type 3 grammars. You get it? Now in type 3 grammars, always you're going to be having only one variable, only one. If the variables become 2, then that's no longer a type 3 language, a type 3 grammar. So let me come back to this set. This is the grammar before. These are the production rules we got. Now when you go to the solutions in the coup, I don't agree with some of their solutions. For example, they're having AS here. You see? For them, they're going to put a very, very fixed state here. This one, let me even put it in a square. They have this. And AS doesn't simply make sense. Because when you have AS, then let me ask you, if you have AS and you start from AS, how can you get A? Only A. There's no way, because when you come and say S is equal to A and S, and then the only way you can't use this production rule to get simple A, because capital S cannot give us epsilon. Epsilon is in capital A, you see? So this rule here, I don't agree. Putting this rule here is the same as saying that we are going to have A here. That doesn't make sense, because when I get A, I'm coming back and I go here. That is an NFA, but I don't think we need to go for that now. We can remove this. And this grammar this is the correct grammar, I believe. The grammar they have in the solution, I don't accept this. Now, a grammar must be a tuple. So what I'm going to do is, my grammar G for that language is going to be A, B, and C. Then I have to, in my grammar I have two states here. I have that and that. I have S and A. Then my first symbol is S, and my production rules are this. The first one is S, can give me BS, can give me CS, can give me A, and the second one is A, can give me A, can give me BA, and can give me CA, or it can give me this. Now what is interesting is when if they ask you for the K grammar, because for the K grammar things are fine, you can read it in the core and see what I'm talking about. This language here can never contain epsilon, so I don't think we need epsilon in our production rules. So there is a simple way to convert this grammar you are seeing here to this. Now this is a regular grammar, but a K grammar is a specific type of a regular grammar. So since A can give us epsilon, so we say we have this A giving epsilon, and these are called null productions because we are producing null. This boy here. So how can we remove this boy here to make it a K grammar? What I do, I come back and I write the grammar as it is. I say S can give me BS, CS, A, then I do that. Now whenever I see capital A, I replace it with epsilon. So no capital A, no capital A, it is yes, I get my A. I come down here also, I say this is small a, capital A, small b, capital B, small c. Now you must don't write epsilon because you are trying to get rid of it. So what I do this, and whenever I see A, I put epsilon. So when I do that, I get A, I get B, and I get C. So this is the K grammar. This is the K grammar. But they didn't ask for it, they just asked, not K grammar, I'm sorry, these are just production rules. So you must write all of this, and instead of writing these production rules, you write these ones, because now, since the language doesn't contain epsilon, we don't need epsilon in these production rules. Now that was part 3 of EXO